Well, thank you, Art, for volunteering to sit down for an interview with us.
You're very welcome. I'm very impressed with what you've done here at the Heritage Museum. It's very impressive work and a very nice way to remember a lot of the things that have happened here, which have been significant at Chalk River over the years.
Good. Could you just give us a quick background of why you came to Chalk River and when you came?
Well, I'm originally from Nova Scotia and did a bachelor and master's at Dalhousie and then went to Caltech for graduate school and in nuclear physics. There was a position for a postdoc here at Chalk River, and I actually met Tom Alexander at a CAP conference, Canadian Association of Physicists conference in Alberta, I believe, effectively for an interview, and received the offer, and we decided that we were happiest going back to Canada to work, and we were. We had a lovely 12 years from 1969 to 1982 here. In 1970, after I'd been here a year, George Ewan, who was a colleague here at Chalk River, moved to Queen's University as head of department actually, and a position opened up. So I was able to obtain that position and had a permanent position here through the 70s and until 1982.
Your career has intertwined with that of George quite a few times. And yes. I guess because of my background in nuclear spectroscopy, always felt that he didn't quite get the credit for lithium-drifted detectors that he should have.
Well, the paper by Ewan and Tavendale, which was the first use of a lithium-drifted germanium detector in a nuclear physics experiment, is regarded as a very historic paper, and he received an award from the IEEE for that, and so he was recognized. But it's one of the things that I try to remind people of. That was a substantial Chalk River innovation. The effect of having germanium detectors rather than the other sodium iodide style that we were using before that was almost a factor of 1,000 in resolution, and that was perhaps not 1,000, about certainly more than 100 in resolution, right. Enough to see individual types of radioactivity very explicitly, which was of value in medicine, but also of value in trace analysis or neutron activation, which of course was the principal motivation for the slowpoke reactor in many cases. So the invention of the germanium detector really revolutionized the use of nuclear radioactivity, as well as making basic science much more accurate.
Right, everyone had to redo all the nuclei effectively.
That's right.
When you arrived, not only did Ewan just go, Harry Gove had just gone, John Keener was just going. It's a whole new turnover and a whole new crop of people that you were part of. Who were some of the other people at that time then?
Who were here? Jim Geiger was a very prominent person here. Bob Graham, Geiger, and Ewan were the ones who developed the Pi-Root 2 beta spectrometer, right. Which was the best or one of the best in the world for studying electrons from electron spectroscopy. Right. There were also John Hardy came here at about the same time as I did and went on to do excellent measurements. Gordon Ball, who eventually ended up as a scientific director at Triumph. Tom Alexander, who hired me effectively, was an excellent scientist, is an excellent scientist who worked on a number of techniques in nuclear physics, developed techniques for measuring lifetimes of nuclear levels that were really quite unique, and he was a very strong mentor for me in the work that I did at Chalk River, and I did many papers together with him. Otto Heuser was a really excellent scientist as well, with whom I worked, and he went on to Triumph also, and did some really innovative work there, and passed away at too early an age, actually. So those were a number of the people that were here, but of course the history had been others that I got to know substantially over the years. Eric Vogt, who was one of the people developing the Triumph Laboratory, and Alan Bromley, who was developing the Wright Nuclear Structure Laboratory at Yale, and went on to be the first George Bush, first President George Bush's science advisor. Very astute individual from Westmeath, as a matter of fact.
Right.
And he had a degree in engineering physics from Queens, and when he finished as the chief science advisor, he was asked to come back to Yale University as the dean of engineering and straighten out their program. They were having some difficulties at the time. So very illustrious group of individuals who were here over the years. The two others that I'll mention, one of whom I worked for, that's Jeff Hanna, very astute scientist, and usually you kind of pass your papers up the line for the assumption that administrators will cursorily look at them and then send them back. No, indeed. And that was Jeff.
That wasn't his style.
He was a practicing scientist in that way, even when he was formerly an administrator. And interestingly, he was a collaborator of Bruno Pontecorvo. And I got to meet Bruno Pontecorvo a year before he passed away, actually. I met him at a conference in Spain, one of the first times he had come from Russia to conferences. It was in 1992. And there was a exhibit of the SNOW project. We were just starting it at that time, Sudbury Neutrino Observatory, at the Expo in Seville, Spain. And Pontecorvo learned about this and very much wanted to visit it. And he was suffering substantially from Parkinson's disease at the time. But he came and wanted me to show him around the exhibit. But even more importantly, he wanted to know how Jeff Hanna and Ted Hinks were. Ted Hinks, of course, had passed away. Not of course, but Ted Hinks had passed away at that time. Jeff was still very active, and he was very pleased to know that. It turns out that those three made a measurement of the neutrino mass using a proportional counter in somewhere around 1950 or so. And it was, I think, a half a kilovolt, which was the best measurement for at least 5 or 6 years thereafter, very astute. But even more significantly, Pontecorvo had a paper in 1948, which was an internal Chalk River document for quite a few years before it was declassified and became public. And in it, he analyzed the ways in which one could detect neutrinos from the sun using chlorine, which of course is what started the whole study of neutrinos from the sun. Ray Davis in the late 1960s used that to study neutrinos from the sun. But in addition, in 1957, Pontecorvo put forward a theory that neutrinos perhaps could change from one type to another, which of course was what we eventually with the Sudbury Neutrino Observatory observed. So he was a very astute individual. He was in the same category as Enrico Fermi in terms of being an experimental physicist first, but someone who was very astute theoretically. and he also proposed ways of determining the other types of neutrinos, observing the other types of neutrinos, muon and tau neutrinos. He could have had several Nobel Prizes for the things that he had put forward if he'd actually been a part of some of the experiments for which the prizes were awarded, Davis being one of them. So he was quite an interesting individual to have been here in Chalk River in the 1940s before he eventually popped up in Russia and was the head of the Dubna facility for many years. And he also is on record at the Deep River Yacht and Tennis Club as the first tennis champion.
Right.
So quite a fascinating individual.
We were fortunate to do an interview with Tom Alexander sometime earlier. He was still quite fine, and I counted something of the order of about 25 publications that you had done with him. And one of them caught my eye was the low solar neutrino flux. And I said to Tom, was that where Art got his beginning interest? But in reading up a little bit more, the interest goes back much earlier.
So when I went to Caltech for grad school, my thesis supervisor was a great guy named Charlie Barnes, who actually was Canadian. UBC was his alma mater, I believe. Very active in the use of the nucleus for fundamental measurements that are relating to, for example, the early days of studies of beta decay that showed that parity was not conserved and things of this fundamental nature. But I worked with him, and what I worked on was higher isospin levels in nuclei and the symmetry that is associated with that, and measurements that would determine whether the symmetries that you observe from higher isospin levels were arising primarily from the electromagnetic force as we knew it, or whether there might need to be some modifications to that force. You can make quite sensitive measurements. So I did that in the Kellogg Radiation Lab at Caltech, which was headed by Willie Fowler. And Willie Fowler eventually won a Nobel Prize for having worked out all of the nuclear reactions that power the sun and other stars, particularly the initial ones that are most prominent in the sun, PP cycle and CNO cycle as they're called. So a lot of the work that was being done by fellow grad students, for example, related to measurements of the reactions that power the sun. And so that certainly the question of how does the sun burn was very much in my educational genes, so to speak. But, in terms of that paper that Tom and I worked on, another person on the paper was Jim Bean, who was here and went on to Oak Ridge, and Haeboon Mack, who was a grad student with me at Caltech and went to Queens and was a substantial part of the successful Sudbury Neutrino Observatory collaboration. Everybody in nuclear physics knew about the solar neutrino problem, as it was called, by 1977 when we published that paper. The question was, was it a problem with the calculations? Were the inputs that went into those calculations, that is, the nuclear reactions that lead to neutrinos being emitted from the sun, incorrect? And that's what that paper was aimed at. We were looking at the possibility of a particular level in a nucleus, I think beryllium-6, which is a very unstable nucleus, but nevertheless, one of the solutions to the problem that a theorist came forward with was there might be a level at a certain place which we showed was not there. Of course, the solar neutrino problem was Ray Davis making measurements with a tank of chlorine, as was suggested by Bruno Pontecorvo, 800 tons of chlorine underground in the Homestake mine in South Dakota, which is now a major underground facility as well. But at the time, he was essentially the only experiment there. He had to measure, I think, 1 or 2 atoms of argon-37 radioactive material produced per month by sweeping it out of this 800 tons with a gas purge, and then putting it into a small proportional counter to make the observations. Really pioneering work. It was a factor of 3 smaller than what was calculated by John Bacall, who was a junior faculty member at Caltech when I was there. I was there from 65 to 69. The first couple of years I was there, they were still working on the final touches of the experiment and what you might expect to have from it. Ray Davis would visit in the summer, and the topic of solar neutrinos was a very big one there. And so certainly in grad school I was very conscious of the fact that he measured something a factor of 3 smaller than what Bacall calculated, as I say, the so-called solar neutrino problem, which is what we set about to measure with the Sudbury Neutrino Observatory.
Right. Your work began to shift a little bit more, and looking at fine structure and a lot of work with Davis Earle.
Indeed. Davis became a very close colleague. He was a staff member here at Chalk River when I was, and but I continued to work with him after I moved to Princeton as a faculty member and the co-director of the cyclotron there in 1982. Davis was a great person to work with. He was a Newfoundlander with a fantastic sense of humor and excellent athlete, top-level ski instructor, and very well-known individual in Deep River. And in fact, there's a scholarship at Mackenzie High School that I created in Davis's name using some of the prize money that was obtained from the Sudbury Neutrino Observatory work, and I hope his memory is maintained by that. But we were working on still fundamental measurements using nuclear techniques to try to look for questions that were going to relate to fundamental physics laws and symmetries that were expected under these laws. We did several experiments at the NRU reactor, in fact, which is where Davis had worked before. But the work that I was doing in the late 1970s, in fact through the 1970s, both here at Chalk River and some work I continued to do at Caltech and at other locations, related to the standard model for particle physics, which at the time had been put forward, and it involved a combination of charged particle called a W for the weak interaction, and a neutral particle, Z particle, which was difficult to define or to determine for sure that it was in fact involved in the way that the theory predicted. And in one case, for the exchange of a Z particle between quarks, it didn't work in the cases where measurements could be made in particle physics that were where it was very obvious that the effects were present, which is with strange quarks as opposed to the up and down quarks from which nuclei are composed. And so the idea was to try to test the weak interaction in nuclei at a very detailed level. And this is difficult because the weak interaction is about 1 million times weaker than the strong interaction. And so what was done was to look for what is called parity violation in nuclear reactions, which is whether a nuclear reaction looks the same if you set it up and try it when it is looking as though it has a handedness associated with it by having spins of particles involved and so on, which looks like a right-handedness, or whether it is different if it's reflected in a mirror, so it would look left-handed. And if you do this, then you can sort out from the strong interaction at levels of a part in a million the difference between, or small differences between, right and left-handed processes. In fact, we set up an experiment at Building 600 using a low-energy electron accelerator that had been that had been developed for nuclear therapy. You yourself, I think, had some involvement in that, and it was actually built by John Fraser and Steve Kidner.
Right.
And Steve continued to work with Davis and myself, and there was an excellent technician, Jack Hill, who worked with us to build a polarized electron source, which was done by the photoemission of electrons from gallium arsenide at ultra-low vacuum. And it had to be very carefully set up in such a way that you could switch from right-handed to left-handed simply by switching the polarization of the light that was used to produce the emission of the electrons. And we were able to use that accelerator with a continuous beam using a technology that had been developed at the SLAC accelerator at Stanford University, which had been developed for pulsed beams. It was the first time anybody had ever done it in a continuous way. And we had very high intensity, much higher average current than is usual. And we were able to do a test at about a part in a million of an effect that had been put forward as perhaps being unusual, actually put forward by a physicist named Lobachov in Russia. And we were able to do that experiment by producing a beam of polarized electrons and looking for the difference between right and left, and we found no effect at a part in a million or so. And so it was really a very challenging technical process, which was greatly helped by the technical expertise here at Chalk River, and the fact that for other reasons there was equipment that was at the cutting edge of electron accelerators at the time. So that's the sort of thing that I worked with Davis on. And then when the SNOW project came along, I happened to be back working at Chalk River with him as we were finalizing that project. And we learned about the fact that Herb Chen from the University of Irvine, California at Irvine, had asked the simple question, do you think it'd be possible to get a few thousand tons of heavy water? Because if we could, then perhaps we'd have enough to be able to observe neutrinos from the sun. And if we could, then the properties of deuterium would enable us to tell the difference between electron neutrinos, which is the type produced in the sun, and all neutrino types, of which there are also muon and tau types, because deuterium enabled you to do those two reactions and tell the difference between them. You had to be very careful because the second of those two reactions could also be triggered by any gamma ray with an energy greater than about 2.2 million electron volts, and uranium and thorium both had gamma rays 2.6 and 2.4 million electron volts that could do the same thing for that second reaction. And so we had to constrain radioactivity to an extreme degree in order to do the experiment, which we were able to do. We were able to purify the heavy water that we eventually were graciously loaned by AECL, and at 1,000 tons, for $1. Good bargain in any market.
There just happened to be a slack in can-do expansion at that time.
That's true. Mind you, when we eventually received it, we had to pay about $1 million a year in excess insurance for
Right.
where we were using it, but that's okay. The project then started in 1984 at Herb Chen's, after Herb Chen's proposal. George Ewan became involved, and he and George were the original co-spokesman of the project. There were 16 of us at the time. Davis was one member from Chalk River, and there were a number of others from Queens and NRC Ottawa and others. And it took until 1990 until funding had eventually been obtained. In the meantime, Herb Chen, very unfortunately, had passed away from leukemia at about age 45 in 1987. And I was a professor at Princeton at that time and took over as the U.S. spokesman in his place. And then at the time that we were working hard to get funding for the project, I had an opportunity for a sabbatical. I took it here in Canada, but also spent at Queens, but also spent a lot of time on site here at Chalk River as we were finalizing the proposal for the project. The final design for the Snow Project, which got approval in the end of 1989, was actually done by Plant Design here at Chalk River, and Ken McFarlane was the lead engineer on that activity. Davis remained firmly involved, and there were a number of others that became involved over the years, including Gwen Milton, Bhaskar Sur, Ted Clifford, and a number of others that were significant participants in the project throughout. So Chalk River Heritage is very strongly involved in the Snow Project. Eventually in 1995, I believe, the mandate for Chalk River became more firmly applied science, particularly reactor physics. And Duncan Hepburn, who had been our initial project manager for the project, being seconded from Chalk River by, at that point, the head of nuclear physics branch, or I guess physics division at that point, Doug Milton, who was another mentor of mine, a substantial degree as when I was here in the 70s. Duncan Hepburn and Davis Earle moved to work for the Sudbury Neutrino Observatory project, but Chalk River also enabled us to have access to a number of pieces of equipment that had been developed here to be used in the project, and so and they maintained the Chalk River component in Snow for about a year after the initial announcement. So we continued to have a very positive relationship with Chalk River on that, and also on the loan of heavy water over the years. It turns out that when the initial request came in, there's a record of the person who received the request from, or the question from Herb Chen, do you think we could get a loan of such heavy water, about 1,000 tons. I think he actually asked for 4,000 in the first place, but that was when he thought the entire cavity would be filled and the shielding would be provided by the heavy water. The answer was, well, probably not 4,000, but maybe 1,000. I think later I learned that 4,000 was pretty nearly the whole inventory. But at that time, Era Meridian was a very senior person at an AECL, and Jeff Hanna was the head of physics division here. And so Cliff contacted them, and there was almost an instant response from AECL saying, yeah, this is a great sounds like a great opportunity. Therefore, I think we could probably engineer that loan, or probably could get that approved. And that was a great impetus to be able to go forward
Yes.
with the project. Still took us a while to get all of the different pieces together from various agencies for I think it was $55 million, the original cost, in 1990. 25% of it coming from the US and about 5 to 10% coming from the UK, and the rest from Canadian sources. But having that support from AECL and also from International Nickel, INCO, who were the owners of the mine,
Right.
who said, yes, we could allow you to do this in our mine. Again, it's often individuals that makes these decisions, and there's a fellow named Walter Kurluk, who was the Vice President of Research at INCO at the time, and it kind of caught his fancy. And I learned later in dealing with mine managers at the Creighton mine, where this is situated in Sudbury, that all engineers take physics in their first year. In fact, from 1991 to about 1994, I taught all the S to Z engineers that came to Queens, first year physics. And they remember and are still grabbed a little bit by what you can do in physics, and that helps when you're dealing with people who
Yes.
have to be convinced that this is a good idea. But George Ewan and Walter Davidson did a tremendous amount of work on convincing various sources of funding. We eventually had help from Ellen Bromley, as a matter of fact, in convincing, ironically, not the people in the United States necessarily, I'm sure he helped there, but Premier David Peterson, who went to Washington for a visit and had his ear bent by Ellen Bromley on the wonderful nature of this fundamental physics project being done in his province. And we were in danger of not getting Ontario funding
Right.
until that happened, and it came through after that. So these, quotes, old boys at Chalk River had a substantial help in getting the snow project to take place.
And it turned out to be a great success. We were able to see what you were looking for, and were rewarded for the leadership in it. And
Yes, I mean, I received they only give the Nobel Prize to one or two people, and they gave it to the people who were the designated leaders of the Snow Project and the Super Kamiokande project in Japan. And I'm very conscious of that, because really there are over 200 authors on our scientific authors, not to mention the tremendous technical background that was applied in building the project, but also the research and development done here at Chalk River and in determining radioactivity levels in heavy water in the early days. We actually traded AECL heavy water with Ontario Hydro in order to get heavy water that came directly out of the lake and hadn't in any way had any small tritium contamination from an upgrade facility that also handled reactor water. But the technical people were a very, very large part of the project, and there's probably over 500 people altogether. So I'm very conscious of the fact that I'm representing a very large group of highly skilled people. So just to tell that story, we received the funding in 1990, started the excavation, built the detector, which consisted of a large sphere of acrylic, which eventually held the heavy water. It had to be built from 120 separate pieces, which were small enough to be transported down in the mine elevator, cage as it's called, which also transported all the people, the miners for their active mining at the same time. It had 2 levels. Each level was enough to hold 44 people standing like this, side by side. Pre-COVID. It had to be loosened up quite a bit after COVID. but it was, I think, 3 meters by 4 meters by 3 meters high, and we had to fit everything into that. So this acrylic sphere was made from those pieces, bonded together in place. First time anyone had ever done that at that scale. This is the first time anyone had ever excavated a cavity size of a 10-story building at that depth, 2 kilometers underground in the Creighton mine. And so there was boundaries of technology that were being pushed all the way along. That acrylic sphere holding the heavy water was surrounded by 10,000 so-called photomultipliers, one of which I have provided to you for the exhibit here, which essentially filled a 18-meter diameter sphere. The acrylic diameter of the sphere was 12 meters, and it was 5 centimeters thick, so it was a bubble, basically. And then the outer cavity, which was 22 meters in diameter, was coated with a waterproof material. First time that had ever been used in that larger scale. It had been developed to prevent radon from coming out of the walls of uranium mines, so that they could coat the walls and flow fresh air from the surface and not have it contaminated by the radon coming out of the wall. It also was very good for added ground control, and it could be sprayed right through the usual ground control. In any case, that was a development of mining engineering at Queen's, and we picked up on it and used it for the first time. And it provided a radon and waterproof barrier into which we put 7,000 tons of ultra-pure light water. Both the heavy water and the light water were purified to about a million times more pure than ordinary tap water. 1 radioactive decay per day per ton of water in the center of the heavy water. So all of this construction took until about 1998, when we started to fill with water, and overcame some difficulties as we were starting out in the project, and with the good physics knowledge of some of our collaborators, in this case David Sinclair, that figured out our problems with breakdowns in our connectors. And that's the value of having a broad collaboration. It's also the value of people who remember what they learned in their second year of physics. That was the reason why we were getting breakdown, in spite of the fact that we'd been testing extensively. We hadn't quite pushed the degassing of the water to the point that we were able to achieve with the full-scale equipment.
Okay.
So in 1999, we started our actual data taking. By 2001, we could release our first results. By 2002, we had the 5 standard deviation, or 1 part in 10 million accuracy of proving that neutrinos did change from electron neutrinos into other neutrino types. Point 1. And point 2, the calculations of how the sun burns were very accurate. We measured them by measuring the sum of all neutrino types, in spite of the fact that neutrinos were changing their type. We could measure the sum that had left the sun, and we knew that to better than 10%, which is of value in terms of validating the same type of calculations that are made for fusion power reactors here on Earth, where you're trying to confine the sun in a bottle, as they say, in this case a magnetic bottle. It's confined within the sun by gravity, and we were measuring it full scale, essentially. And so very often you find that you set out to do a basic science experiment and you end up with something that's of value for industry. Certainly that test of the coating in the walls was a valuable contribution. The first excavation of the cavity at that depth, and the supplier of the acrylic now builds aquaria using similar techniques that they developed, which they thought they might not be able to do in the field or directly on the aquarium site. They now do them routinely, and so they learn from the process as well. So science and technology very often go hand in hand, as people know very well here.
I do the quick calculation, and you've been involved in physics in some form or another for somewhere of the order of 55 years, but I don't detect a decrease in the enthusiasm. What's next for art, and what's next for snow? Or the snow lab, anyway.
Okay. There's an answer for snow and an answer for the snow lab. And for me, so I'm here, as it happens, at this time for a collaboration of the DEEP experiment, which is dark matter detection with argon, DE, dark matter experiment with argon and pulse shape discrimination. That's where DEAP comes from, in which people from Chalk River are participating still, which is very valuable for us. They contributed to the definition of ways of vetoing the muons, which are the cosmic rays that manage to penetrate and trickle down even after the 2 kilometers of rock. They're 1 million times lower than the cosmic rays on the surface of the Earth, which is roughly what gives you the northern lights, is their interaction in the atmosphere, right. And our detector would light up from them either in DEEP or snow. So they contributed to that, and I just saw this afternoon how their expertise in muon tomography is being used in other ways, in other practical ways, looking for various dense materials of a nuclear nature and a nuclear security type right. of process. So again, science and technology come together. So I'm involved in that experiment. It is an attempt to look for dark matter particles, and that's become a big topic in right. The field we call particle astrophysics, which is doing astrophysics using particles, as you might guess, sometimes called astroparticle physics too, where neutrinos we discovered by seeing that they change their flavor do have a finite mass, but that mass is very small. Current limits are on the order of 1 million times smaller than the electron mass. The dark matter is something else. It's not neutrinos. It was thought in the first place that it might be, because it behaves in some ways like weakly interacting massive particles. And scientists love a little bit of whimsy, so, right. So we're looking for WIMPs.
Right.
Dark matter is very well known as of the last 20 years to have a substantial influence on our universe. Measurements that have been made with astronomical instruments, measurements of and calculations of how galaxies and other large-scale structure forms in the universe, they indicate that you need a fairly massive weakly interacting particle, or many other forms right. that are put forward, but that's the dominant one. And they're weakly interacting, therefore they pass through the 2 kilometers of rock. You have to build large detectors in order to detect a very low rate of these. And the DEEP experiment is a prime example of that type of detector. It uses liquid argon. Nuclear recoil gives out light very quickly, background radiation very slowly, and we end up with a ability to discriminate against that. So the DEEP experiment is 3 tons of liquid argon, and we have looked at the first 230 days of data taken with that experiment and saw no events, either from background or from dark matter particles, and we were able to set limits that are quite respectable as these things are measured these days. And we're now pushing on to improve the experiment and get rid of what we think are backgrounds that might interfere if we count longer, and we'll restart again next year with an improved detector. So it's an ongoing project.
Okay.
But at the same time, there's another experiment in Italy, in an underground laboratory under a high mountain there, Gran Sasso Laboratory, which uses 20 tons of liquid argon. And so for the last 2 years under COVID, I've been the chairman of the what's called the institutional board for that project. The project has 450 scientists in 16 countries, about 70 different institutions and 15 countries involved in it. And so that was a senior management job on the project. I've just finished my term with that. But essentially all of the people involved in the DEEP experiment have also signed up to be participating in that. And the collaboration as a whole has targeted SNOLAB as the location for another experiment yet 10 times more substantial than the one we're building. In other words, 100 times, 300 tons, 100 tons
liquid argon.
of liquid argon, obtained from an underground source so that it's low in radioactivity. And that's been targeted by the collaboration to go into SNOLAB 10 years or so from now.
Uh-huh.
So I'm still active in that, also somewhat active in the rejuvenation of the SNO experiment, which is now called SNO Plus and led by Mark Chen, a professor at Queen's University. Replacing the heavy water with a liquid scintillator that gives you 50 or more times greater light output, in which there will be dissolved some tellurium, tellurium being one material for which an isotope, tellurium-130, can participate in what's called neutrinoless double beta decay.
Uh-huh.
So the energetics of beta emission, electron emission, actually electron and neutrino, they usually go together in beta decay, from a single beta and neutrino emission from tellurium-130 is energetically forbidden. The relative masses of the nuclei involved prevent it. Whereas a 2 electron and 2 neutrino emission is energetically favorable. Just the way the nuclear structure defines the relative masses. So it's one of about 20 favorable cases for looking for this phenomenon of neutrinoless double beta decay. What has been observed already is the emission of two electrons and 2 neutrinos, which is the normal beta process taking place twice. And that's a continuum of electron energies, just as is for a single beta decay. However, if a neutrino has a finite mass, which we now know it does, and if the neutrino is its own antiparticle, which is also a possibility because it's has no electric charge, that would normally change if you went to an antiparticle. It doesn't feel the strong interaction, and it only feels the weak interaction. And it is possible, therefore, that the only difference between a neutrino and its antiparticle is, in fact, their spin, right-handed or left-handed. But if they are what are called Majorana particles, they are their own antiparticle, or at least they can be described in a way that allows that to be a process. Then, rather than 2 neutrinos being emitted, you can have annihilation within the nucleus and they don't get out. In which case you have a energy release between the 2 nuclei which is entirely represented in the 2 electrons. It's not a continuum which is caused by the emission of neutrinos at varying angles and energies and so on. But you just have the 2 electrons being emitted. Sum up the energies and you get a peak at the end of the spectrum for two neutrinos for two neutrinos and two electrons being emitted. So that peak is what we look for in this experiment, and tellurium-130 is a 36% naturally occurring isotope of
Not too
tellurium.
bad.
So you don't have to go through the expense of trying to enrich
Right.
the isotope in order to do the measurement. And so we're prepared. The experiment SNO has been reconfigured, which took a fair amount of work because the liquid scintillator that we put into which the tellurium will be added in about 2 years' time, when we have a fully purified amount of about 4 tons of purified tellurium. The liquid scintillator that's been put in there is lighter than water instead of heavier than water. So previously we had that acrylic sphere held up by ropes, because obviously heavy water is
Right.
heavier than the water that surrounds it. Liquid scintillator is lighter, lower specific density, so you have to hold down the sphere. So we had to drill holes, 10 holes in the floor of this beautifully clean coated cavity and put ropes over. It's a beautiful example of macrame, actually.
Right.
And it's now running again after recoating a large fraction of the surface, as well as doing the drilling in a clean way. And it's running with liquid scintillator. We're studying solar neutrinos again with that. We're studying neutrinos from the Darlington, Pickering, and Bruce reactors, looking for oscillations of those neutrinos. We're studying neutrinos from the Earth. They're actually anti-neutrinos, for which the hydrogen is an advantage, the hydrogen in the liquid scintillator. And we can study uranium and thorium deposits down about 600 kilometers. Uranium and thorium, it turns out, represent about 40% of the heat output in the Earth.
Okay.
And so the geophysicists are very interested in being able to study this
Get a
well down
handle
into
on
the
that one.
mantle. Yeah. So we're doing geophysics as well as neutrino physics. So it's a multidimensional experiment, but it'll be very interesting when we get to the point of looking for neutrinos double beta decay, because that process of neutrinos being their own antiparticle figures prominently in theories that potentially can explain what happened to all the antimatter in the early universe, where we think the Big Bang made equal amounts of matter and antimatter, but this universe is dominated by matter.
Right.
You don't see positrons except when they're emitted in radioactive sources.
Right.
And so there's a process that created an asymmetry back then. Neutrinos are thought to be a part of that, and in fact they're called leptons, and so the term leptogenesis is the term that's used for what happened in the early universe. We hope to understand that by making these measurements, of which the SNO Plus experiment will be among the most sensitive. 2 of the other very sensitive experiments are slated, the scientists have stated that where they would like to have them situated is in the one remaining empty cavity at SNO Lab. And so SNO Lab has a substantial future in terms of this, in terms of dark matter. And so I now realize that I haven't said how SNO Lab originated, so let me go back and correct that. Our results from SNO came in predominantly in 2001 and 2002, although we continued running until 2007. But in 2003, the Canada Foundation for Innovation put out a call for laboratories built in Canada that would attract significant international participation here in Canada, and put $100 million on the table for this purpose. And again, David Sinclair and Carleton University submitted a proposal. Many of us worked on it, but that was the leadership provided, and received about 39 million of that 100 million, and developed a laboratory which is about 3 times the excavated volume of the original SNOW project on the same level, 2 kilometers down. And there are over five or six experiments there now studying dark matter. Some of them using argon, as I mentioned. Some of them are looking for dark matter particles to collide with silicon or germanium, and they have techniques for discrimination in this case. Others look for bubbles formed when the dark matter interact in a superheated medium. That's called pico, and it uses fluorine predominantly. Another one, NEWS, is using light gases. And so we're looking for dark matter in a wide variety of different locations using different techniques to suppress background. And so it's become a very active, continues to be a very active laboratory, and as I say, is attracting the interest internationally of people who want the deepest and cleanest, or let's say lowest cosmic ray flux. And it's the only laboratory in the world where the whole laboratory is class 2000. So it's been a big success.
Great.
And in fact, just yesterday I attended, not yesterday, Friday, I attended an underground ceremony where the Minister of Industry, Science and Innovation announced 5-year funding for the laboratory. So
Fabulous.
on the order of $100 million to have it continue to proceed. So the SNOW project generated a strong legacy.
Right.
And there's also an institute that was formed, which is headquartered at Queen's, but is across the country, which was funded by a Canada First Research Excellence Fund of $63 million over 7 years. It has funded 15 new faculty members in this field across the country, spawning about 10 or a dozen more faculty members in the field as well, and about altogether 7 or 8 universities across the country. It also has supported over 200 postdocs and students, and has a substantial outreach program and educational program, equity, diversity, and innovation, equity, diversity, and inclusivity is a substantial part of what the Institute does. So both from the hands-on technical aspect of things and from the new generation intellectually, Canada's in a great shape for pushing on from what the SNOW project originally did. And I'm just very pleased to see this next generation
Yes.
doing such good things. So there's a future in this field for Canada because we can provide some of the best facilities in the world. And of course, the ability to do that was in the first place stimulated by our collaboration with Chalk River. Perhaps one other thing I'd like to mention is the fact that starting right at the beginning of COVID, we were able to bring together scientists from the dark side experiment, together with scientists and engineers across the country, in which Chalk River played a very significant role, as did Triumph and SNOW Lab and the Institute at Queen's University in this field of particle astrophysics. In building, in response to a Canadian government initiative, a new type of ventilator which is targeted at intubated patients in ICU units, the last stages where you absolutely need ventilation. The problem in the early stages of COVID is that the ventilators that were available were very expensive and multi-purpose, such as you might find in hospitals for a wide variety of things, but the numbers that were being needed for COVID patients outstripped the numbers available. And so what was needed was a low-cost, easy-to-manufacture ventilator. And so about 200 scientists came together for about 8 months, including about 25 people from Chalk River, engineering and technical people, One of the leaders here at Chalk River was Mitch King, who was the overall integration engineering leader for the project. But we were able to put together a device which really had only about 50 main components, which helped the supply chain issues very substantially. But we certainly learned very quickly the difficulties of trying to produce a medical grade instrument. So we were helped greatly also by people from CNL, mainly in Fredericton, who do software development for nuclear reactors, where the stringent requirements for ISO standards are similar to the ones that you need to have for medical devices, go far beyond the protocols that we use when we're building equipment in our experiments, which are only for, let's say, mechanical use in our own case. So Chalk River really provided a substantial contribution to that project, and ultimately we provided over 7,000 ventilators to the Canadian stockpile. After a lot of work with a Canadian company, Vexos, and another one, JMP Solutions, and a lot of work in satisfying Health Canada and their authorization process, which tests at Chalk River and modifications suggested by people at Chalk River were very instrumental. So it was a response to COVID that I think everybody that worked on it worked long hours merely to be able to make a contribution. And Chalk River was very prominent in that. So it was a real pleasure to work with people at Chalk River again in such detail.
Yes. Excellent. Well, thank you very much for sitting down with us, and continued excellent health to be able to take part in those next 10, 20, 30 years worth of effort that we can see being on the boards.
Thank you.